Now, to investigate the Pythagorean identities, we can basically build them. Remember this picture, we've looked at this before. In the beginning, we called this a unit circle, and we said, imagine that this has a radius of 1, and so our hypotenuse of our triangle here would be 1. Now, we've dropped a line straight down from that point so that it meets the x-axis at right angles, and labelled the acute angle theta. Now, we can take this one step further to say, what if it wasn't a unit circle? What if the radius was more than 1 or less, for that matter? Could we, in fact, just label it r for radius? All right, can we also label the other sides of the triangle? Now, if this is the point xy, it means that to get to here, you've come across x units. So the length of this side must be x. And for this to be y, this length here must also be y. Now we have a little right-angled triangle, we can go ahead and write down Pythagoras' theorem. X squared plus y squared needs to be equal to r squared. All right, what next? Well, next we're going to change the form of this. We're going to divide everything here by r squared. Why are we doing it? Well, we're taking what we know here and we're seeing if we can rearrange it to make it look different. So if we divide the first term by r squared and the second term by r squared, we need to also divide everything on the other side by r squared, and r squared divided by r squared is just 1. All right, what next? Well, don't forget that if you have something squared over something else squared, that's exactly the same as just having that fraction and squaring the whole thing, isn't it? They're equal. So think, this is basically x over r, all squared. Now what is x over r? Well, let's refer back to our picture. X over r, well, that actually looks like a trig ratio, doesn't it? That looks like the cosine of theta, because cos theta is adjacent over hypotenuse, x over r. So this really could be rewritten as cos theta, all squared. Now when you have a trig ratio and you square it, you don't put the square sign up there. The reason is it can be confusing and you would need brackets to make sure you know whether it's all of cos theta squared or whether it's the cos of theta squared. And somebody way back when probably just decided that to save the confusion and to save the need for brackets, if you're squaring the whole of cos theta, you just put the squared in there. And that means cos theta squared. All right, for this one we have y over r squared. Now y over r looks like the opposite side over the hypotenuse. So that would be sine of theta, all squared. And here we can just literally label that again as 1. Now we've made our first Pythagorean identity. Now you can put a box around it like that. I think I prefer to write it with these two the other way around. Don't ask me why. I guess when I first learnt trig, I learnt sine, cos, tan, and I find it easier to memorise this with the sign first. Obviously it doesn't make a difference. You're adding two things, so it makes no difference what order you add them in. But that is our first trig identity, and that's the one that you need to memorise, because if you memorise this, you can basically use it to build the other two. How do we do that? Well, how could we fiddle with this to change the look of it? Up here we fiddled with this by dividing by one of the terms. So down here, it makes sense that if we divide by the sine squared theta or the cos squared theta, we can make this thing look different. So to build our other two trig identities, we're going to take the first one and we're going to either divide it by sine squared theta or cos squared theta. Let's see what happens to each term. If we take sine squared theta and divide it by itself, we get 1. If we take cos squared theta and divide it by sine squared theta, you can think over on the side here, what is cos over sine? Well, sine over cos is tan, so cos over sine is cot. So this gives us cot squared theta. And for the last term, we're going to have 1 over sine squared theta. If it helps you to jot it down over on the side here, then go ahead and do it. 1 over sine, that's a reciprocal ratio, isn't it? So it will be cosec theta squared. Okay, so that's our second trig identity. We built it from the first one by dividing everything by sine squared theta. Let's now ignore this and go back to our first one and divide everything here by cos squared theta. All right, sine squared theta over cos squared theta. Sine over cos is tan. So that will give us tan squared theta for the first term. What about cos squared theta divided by cos squared theta? Well, that's 1. And the last one, we need to do 1 divided by cos squared theta. Well, 1 over something, that's a reciprocal ratio, and the reciprocal of cos is sec. So we have sec squared theta, and that gives us our last Pythagorean identity. Memorise this one, know how to build those two. If you can memorise all 3 of them, that's fantastic. But one thing to bear in mind, we have everything here. Sine, cos, tan, cot, cosec, sec. They all appear only once in these 3. So if you're trying to prove a trigonometric identity using one of these, or you're trying to rearrange an equation so you can solve it more easily, if you find any one of these, and they have to be squared, okay, like this, then you can use it to rearrange and build, to change your identity, I suppose, into something else. For example, if you had sine squared theta and you wanted to find something else that was equal to, all right, then here, taking this identity, well, if you want to get sine squared theta on its own in this equation, you'd have to subtract cos squared theta from both sides, wouldn't you? That would give you 1 minus cos squared theta on this side. So it stands to reason that sine squared theta is equal to 1 minus cos squared theta. Similarly, if you wanted cos squared theta on its own, then you could take this equation and subtract sine squared theta from both sides, and you'd get this. So if either of these two pop up in an equation and you need to change them to these, you can. Or if either of these two pop up in an equation and you need to change them to those, then you can. And that's how we generally use them. Now, one other thing to mention quickly with these is that we know that cosec is the reciprocal of sine. So if you found that sine of theta was equal to 0, then the cosec of theta would actually be undefined. So this only works if sine theta is not 0. Similarly, sec's reciprocal ratio is cos. So if cos theta was equal to 0, then when you flip that upside down to make sec theta, or sec squared theta, that would be undefined, and this wouldn't work. So that's just 2 things to keep in mind. Sine of theta can't be 0 in this case, and cos of theta can't be 0 in that case.